All right, and the timer. Okay. So let's start with the brief summary of the geometry of Möbius transformations. Now here, there was a question by George, which was, if you give me a parabolic transformation, that is a Möbius transformation with exactly one fixed point in C bar, whether the degenerate Steiner grid, whether it's Steiner grid, which would be a degenerate Steiner grid, is well defined. And the point is that we conjugate. It is well defined. Let me just quickly say why it's well defined. So we conjugate our parabolic Möbius transformation is conjugate to a translation, but we know that all translations are conjugate. Right? But now the point is that each translation has, of course, a well-defined translation direction, right? So the family of lines, of Euclidean lines that are stable under the action of that translation, that one for each translation is completely well defined. Yeah, and then it's very easy to prove that when you pass through to another translation via conjugation, that family of stable lines, of lines that are stable under the action of that translation, has to go to the family of lines that are stable under the other translation, which means that when you kind of go back to the original parabolic transformation, there is the family of circles that are, each of which is stable under the action of the parabolic transformation, is well defined, because here the one that is that is canonically defined for one translation vector goes to the one that is canonically defined for the other translation vector under whatever conjugation you have of them. Yeah? And hence in you conjugate your parabolic transformation with the one fixed point to one, and then the family of circles, is each of which is stable under the transformation, is well defined. And then the other family, which we took kind of arbitrarily, said take the orthogonal one, then just has to go to the orthogonal one. Okay, so that's pretty much the reason that when you just consider translations and how they and any conjugating transformation between them in MÖBC, this one goes exactly to this one. That's the reason in the end. And now also that to study the geometry of arbitrary Möbius transformations, somehow the two key points were, or the two key ingredients were, conjugation in MÖB and the standard examples, and that every Möbius transformation is conjugate in MÖB plus C to a standard example, because then it suffices to analyze the behavior in the standard examples, the geometric behavior of them, and then we know that the conjugating transformation lives in MÖBC, so it's conformal and it sends circles to circles and preserves angles. Yeah. So for instance, for translations, like as you are seeing here, let's say what I mean by this picture is that if you take a point here, then you translate it, yeah, and then you send through the conjugating transformation, and this means that whatever point that corresponds to this one has to be sent to another point. So somehow, in a way, I'm saying that you just take the behavior here and map it through completely through the conjugating transformation. Like same thing here, where here somehow here let's see, here I'm intending to illustrate the parabolic ones. Here the elliptic. Yeah, and then somehow here these are the stable the stable circles. Yeah, and somehow what I mean is here if you take one of these rays and then it sends to another ray, then you know what happens in the picture here that somehow I didn't complete, and I think if I try to do it live, the picture here is going to be really ugly. So I'm going to leave it as an exercise to fill this in, right? To fill if this is the behavior. If you draw the behavior for the standard example here, the exercise is to fill this in. So fill this exercise. And same thing here. I'm going to say just to save time. Yeah. By the way, multiplying by a non-zero complex number, by a non-zero non-one complex number is always conjugate to multiplying by its inverse, right? And the conjugating is just switch the two fixed points, which in this case are 0 and infinity. So it's 1 over z conjugates multiplying by alpha with multiplying by alpha inverse. Okay, so all of these are exercises, yeah. Which in any case we saw like some animations of how this behaves, right? How this behaves. So yeah. Now, what happens when the Mobius transformations themselves? Yes. So, sorry. This. Yeah, okay, so that's there, yes. The previous one, I think it was not. Yes. Yeah, but this one is there. So how about the Mobius transformations that are parabolic, elliptic, or hyperbolic, or in principle loxodromic, and preserve U? So one exercise is that if you take a loxodromic transformation, it doesn't preserve any disk in C bar. So you give me a loxodromic Mobius transformation and any disk, and this let's say that the Mobius transformation is nu, and the disk that you are giving me is D. So nu of D is always different from D. It never preserves. So it's only parabolic, elliptic, and hyperbolic that have a chance of preserving U. And now, when they do preserve U, which we saw are precisely when they come from matrices in SL2R, and actually there's a same like as before, taking associating to each matrix in SL2R, its Mobius transformation. Yeah. If we take the image of this, so this is the previous map that to each matrix associates its Mobius transformation. So this is like this mu. If you take the image of mu under this, so mu of SL2R. Yeah, it's precisely the Mobius transformations that preserve U. That's what we already saw in the last lecture. But actually, when you consider this, that, I don't know, it's kind of tempting to say that this is mob plus of let's say of u, and then you just consider this SL2R. This induces an isomorphism between between this mod plus of u and PSL2R. Yeah. Okay. Now the three types, parabolic ones. Okay, the parabolic ones. If you think about horizontal translations, they preserve u bijectively. Kind of, it's very easy to imagine their geometry. But how about the other ones, right? So that's kind of more challenging. The ones whose fixed point is not infinity. So the first thing to notice is that if you give me a parabolic Mobius transformation that preserves u bijectively, parabolic Mobius transformation that preserves u bijectively, yes, then the fixed point has to be in R bar. That's the first thing. The fixed point is in R bar, and second, it behaves like either in the clockwise sense or anti-clockwise sense. Each of the tangent circles is stable. So each of these is stable under the action. And actually, because of conformality, you know, like if you take one of these semicircles orthogonal to R bar, the image of each of them is another one of them. So at least according to the way I'm drawing things, somehow here I would be thinking that my parabolic transformation is kind of behaving in a counterclockwise sense, and then I'm saying, okay, the image of this one is this one, and then let's say again, and then again, and then again, and then again, etc. So I'm kind of repeating myself with respect to the previous lecture. Yeah, and then sending like this to this accordingly, to this accordingly, to this. I don't know if the vertical, but to this one, etc. But so somehow that's how the parabolic ones look like, kind of somehow like flowing this way in a way, but of course flowing discretely. Now the elliptic ones look like this one. So first of all, now you give me an elliptic Mobius transformation that preserves u bijectively. So it has two fixed points, and one thing one proves is that the two fixed points, that none of them lies on R bar, first of all, and second, that as complex numbers they are conjugate. So here you would be seeing one fixed point, and the other fixed point of the parabolic transfer of the elliptic transformation would be the conjugate complex number. And then here again, the elliptic transformation behaves either kind of with respect to these circles, which are Apollonius circles of the two fixed points. If you look at the ones contained in U, it behaves like somehow like rotation. So either clockwise or counterclockwise, and then somehow, like for instance here again, thinking that that is like counterclockwise, somehow is something like one such semicircle orthogonal to R bar would go to another. Sorry, I drew things way too close to each other. So somehow this one would go to another one that has to pass through the fixed point. yeah, and somehow you know the angle that they form here is the angle of the alpha, of the multiplication by alpha. In other words, the angle between this tangent and this tangent is precisely alpha. Okay, and then if you keep applying, here I'm doing things counterclockwise. Then somehow you keep moving, and then here my picture is really not good, and so on. And then at some point that doesn't look orthogonal at all. Yeah. Okay. Sorry. I'm not good at drawing, and I'm worse when it's live. So something like this, and it kind of, in a way, it looks like it returns, but then of course it may not close perfectly, right? And it closes perfectly. It closes perfectly precisely when the angle of rotation is a rational multiple of 2 pi. Okay, and finally the hyperbolic case. Again, if now you give me a hyperbolic Mobius transformation with that preserves U bijectively, first of all, the two fixed points, well, they are different, but both of them lie on R bar. That's something you can prove, and then one of them behaves as an attractor and the other one as a repulsor. So here, let's say and again, it could be, at least in this case, it could be from left to right or from right to left. Yeah. For instance, if nu is it looks like repelling from this and attracting to this, then nu inverse, of course, has the opposite behavior. Right? Okay, and then the behavior is on these are the common circles. Yeah, and now if I consider the Apollonius circles of the two fixed points, they are semicircles orthogonal to R bar, and if this is the repulsor, then somehow they begin getting away from one, yeah, and then then getting close to the other, always being Apollonius circles, right? So in particular, always having this, and then like for instance with this drawing that I just did, in particular I would be saying also this point goes to this point under the first iteration, to this point under the second, to this point under the third, under the fourth, etc. Yeah. Okay. Yeah, and so this is the behavior of all the possible behaviors of Mobius transformations that preserve U bijectively. You can just translate it to the disk, yeah? Where the disk maybe, let's say, in the case of the elliptic ones, the relation between the two fixed points is that they are inverse to each other according to classical inversion. Yeah? So like you have the Euclidean center here, and so the product of these two distances is 1. Yeah? So that's the relation between them. What other thing to notice? Here the nice thing is that somehow the family of circles preserved by my parabolic transformation, they look really nice in the sense that they are all tangent to this circle, and you see kind of as you let the radius increase, the Euclidean radius increase, they really somehow converge to actually the circle somehow. That's a nice feature. Something similar here for the common circles of these two. If they somehow really seem to converge to this one, and here the nice thing is that you can see the whole behavior as kind of flowing discretely from the. Now I wrote I still wrote the repelling one on the right, kind of like this. Okay. Yeah. Okay. So now let's properly begin with actual hyperbolic geometry. So I could have skipped Minkowski's hyperboloid, but I haven't, because somehow for me it's the one that presents the Riemannian metric in the most natural way. Yeah. So we start with the Minkowski's form, yeah, which is the defined on R3, and is almost the usual dot product of vectors, except that the third entries are matched but with a minus sign. Yeah? So that's kind of the only difference with the usual dot product. It's of course bilinear. It's of course symmetric, right? If you switch the two vectors, you get the same thing. That's obvious, and it's non-degenerate. And by not, what does it mean to be non-degenerate? It means that by definition that the only vector that has the property that matched with everything, with anything, is zero, is the zero vector. So there is no non-zero vector that has a pairing equal to zero with every single vector. Okay, but it is not an interior product. It's not an interior product because what fails is that it is not true that for every non-zero vector v we have this different from positive. This is not true. So this is not true for every v. Yeah? I mean, you can easily construct a vector with the property that paired with itself is zero, right? I mean, just like, let's say, with this.
So this is the definition of the interior product.
No, interior product is what is R bilinear, symmetric, non-degenerate, and with the property that for every non-zero vector, the pairing with itself is positive. Because the pairing with itself is positive, so that its square root will give you its length. Okay, so it's not an interior product on R3, but we will see that it's not actually not that bad. Now, being a bilinear form, a bilinear function, it has an associated quadratic form, which is the function defined by on each vector, it's just pairing it with itself. Yeah. Okay, so now for each real number, I think as just in calculus of several variables, for each real number, I ask myself about the level set corresponding to that number, which is just the pre-image, right, or the fiber according to the map. Yeah. So it's this by definition, right? So all those with the property that the value is that constant, and you see, one can. This is really easy. That this set is the surface of revolution of this planar curve, which you see leaves kind of it's like a vertical. It leaves vertical, right, in the YZ plane. So it leaves vertical, and you rotate it around the x-axis. Yeah, and what you obtain is precisely the level set. Okay, so we can see we can see the shape of this very easily if we see the shape of this in the YZ plane. That's the whole point. Like I'm going really back to undergrad math. Yeah. And I'm not going to go through all this. Just that then the level sets there are three different types of level sets, which is when z is negative from negative to zero, which in the ZY plane ZY plane, they look like hyperbolas that open vertically, either far from the origin, right, or very close to the origin. Yeah. When C is positive, it's hyperbolas that open horizontally. Yeah. And when C is 0, is just this, just the Z equal Y and Z equal to negative Y lines. And at least, for instance, this can be seen very easily. Here, if you make this equal to 0, then what happens is that Y square has to be equal to Z square. So Z and Y have to be equal in absolute value. So the solution of that is just this. Okay, and otherwise, if you want to go into detail, like really into detail of why these curves look like this, it's all here. It's just a change of basis. But so you see, for C negative, I have when I rotate vertically, which is what I said we would do, I obtain a hyperboloid of revolution, and that is for that value of C, right? So that level set for that value of C. For C equal to 0, it's also very easy, right? You just have to rotate the two lines. You obtain the so-called light cone. And for this other one, the thing is, you see this, when you rotate this side of the hyperbola, it maps precisely onto this side. So what you obtain is a one-sheeted hyperboloid. And we are going to, okay, this is another picture, kind of nicer than the one I drew from Penner's book. And we are going to take, -1, which then we saw that it's a hyperboloid of a two-sheeted hyperboloid of revolution. But then we are going to take only the upper part, so only the upper sheet, and I'm just going to call it the hyperboloid. So even though I'm taking only one of the two sheets. Okay. So the thing is, so here's the description, and then I solve for Z in such a description, and what I obtain is that then X and Y, I can set them to vary freely, and then Z is equal to this, where of course I take the positive square root. So this is the description as a parametric surface. Yeah? So that's the thing which allows me to control it to simply the plane. Yeah? Unfortunately, the whole thing is a parametric surface. A proposition, which is not hard to prove, is if you want to compute the tangent plane at any point explicitly, explicitly as a subset of R3, it's quite easy. You take the point in the hyperboloid. You want to compute the tangent plane explicitly. It's precisely the orthogonal to your point under Minkowski's form. So quite easy to find. Yeah, the proof is quite easy. Because one knows that both of them are two-dimensional. Okay, so it's kind of okay. Why is this two-dimensional? Yeah, it's not three-dimensional because the form is non-degenerate, so it's at most two-dimensional. But why can't it be one-dimensional and so on? Well, because it's the kernel of it's the kernel of a certain map, so it has to have dimension 2. Dimension 2. So to show that they are equal, one only needs to show that one is contained in the other, and one does that, right? So using precisely the fact that we have a parametric description of M. So one shows it just directly and using the fact that the form is super explicit and kind of very easy to manipulate algebraically. Okay, so one has an explicit description of the tangent plane at every point as a vector subspace of R3, and then the theorem is that for each point in the hyperboloid, when you restrict Minkowski's form to the tangent plane, it is an interior product for the tangent plane. So in other words, the Minkowski's form is not an interior product for the whole of R3, but it is an interior product for each of the tangent planes that are of interest to us under the hyperboloid. And the proof uses the famous Cauchy-Schwarz inequality, and it's quite simple. Maybe I don't want to read the proof, but it is really easy, right? So one has to check, given P, one has to check that the interior product, that Minkowski's form on any two tangent that Minkowski's form of any tangent vector against itself is positive, which is this, yeah, and then like a kind of you just check it. Yeah? I don't want to stop to do this in full detail. I prefer to keep going. Just that then what we have is two things. One is that again, I repeat myself, for each point in the hyperboloid, bless you. So I have the hyperboloid. I have a point. I have the tangent plane, and on this tangent plane, Minkowski's form itself is an interior product. Yeah, and then let's say on the tangent plane, I can fix canonically or let's say standardly a basis because my surface is parametric. So I can just take I can just take the image of 1, 0 of 1, 0 and 0, 1 in the tangent plane for every point. Yeah, and then see what the interior point what the interior product on the tangent plane looks like with respect to this basis, and it looks like this. So for each point, if for this point for each point on the hyperboloid, with respect to the standard basis of its tangent plane, the matrix of the interior product is precisely this one. And what's the point of this one? Well, it allows me to see that it varies smoothly on the parameters. So really what I have is a Riemannian manifold, because I have a differentiable manifold and an interior product on each tangent plane, and this interior product varies smoothly as the point varies. Okay. So this is a Riemannian manifold. Yeah, and now I'm going to move to the disk. I could do a lot more on the hyperboloid. On the hyperboloid, I could actually compute fully computed the group of Riemannian isometries, for example, and describe explicitly the shortest curves, or if you want, the geodesics. This I could do, but I'm going to skip it. And it's really quite beautiful, but I'm going to skip it for time constraints. My whole point of at least for this course, in mentioning the hyperboloid, was to see that it comes equipped with a natural Riemannian metric, coming from coming from the Minkowski's form, which is really like almost the usual dot product. So that was my point, that it really comes equipped with an interior product for each tangent plane by considering a really slight variation of the usual dot product. Okay, now what I'm going to do is I'm going to pull this Riemannian metric from the hyperboloid to the disk. Yeah? And for that, first I need a diffeomorphism from the disk to the hyperboloid so that I can pull it back. And well, I'm going to do just stereographic projection, but now from 0, 0, minus 1, which I can think that it's still the south pole, right? And you can even think that it's the south pole, you know, lying on the other sheet. Anyway, I do the same that I did between C bar and the unit sphere, but now I do it only between the unit disk and the hyperboloid. And it turns out that they define mutually inverse homeomorphisms. Given by these rules, one can give the rules precisely. This is very easy, just with basic linear algebra. And these rules allow me to see that they are actually diffeomorphisms of class C infinity. So I can pull back the Riemannian metric, and I will do it in a second. Yeah. So here, for instance, is an example of how the image of a circle segment orthogonal to the boundary, its image under the stereographic projection looks like this one, like this curve. Okay. This, I really like this picture that I found in a tweet, because I don't know, to me it really gives me the idea that it's kind of that this guy is seeing with hyperbolic eyes. Yeah, but okay. Okay, so now this is a diffeomorphism. This is the derivative. Yeah, these are mutually inverse diffeomorphisms, and this allows me to pull back the inner product, the Riemannian metric. So now really the Poincaré disk is not just the unit disk, but the disk with the Riemannian metric that I obtained by pulling it back from the hyperboloid. How do I pull it back? Well, if you give me a point in the Poincaré disk, yeah, here I was supposed to include a picture here and I forgot. Yeah, so maybe let me try to include it from here. Let's see if this would work. Let me see if it works. Okay, so if you give me a point there, let's say, and now I have to change color. Yeah, I don't know, let's say here. Yeah, so that I have its tangent plane. So let me draw it. Its tangent plane. And what can I do? Well, I can send the point. I can send it through stereographic projection, and it's some point here, and it's a diffeomorphism. So I know that the image of that tangent plane that you are seeing is precisely the tangent plane here, which that would be really hard to draw. Yeah, because it doesn't look tangent at all. But and then I want to define the dot product between vectors here. Well, what can I do? Well, send through the derivative, And here you have a dot product between them defined. Okay, just do that, right? So the standard construction works. I mean, not works. It's like I just described the standard way of pulling back a dot product, or if you want a form on the target, yeah. This makes of D a Riemannian manifold. Okay, and then of course one can ask, yes, but give me the precise formula for this in terms of the point of the point you are anchored at which you are anchoring, and the tangent vectors. Well, here it is, right? And how do I do it? I mean, it's really just direct computation, yeah, which I've done. I mean, yeah, and it's a bit long, but what you see, yeah. Okay, so now we have our metric, and now I mean what I like about this approach is that okay, then the thing is, I'm just pulling back some interior product that I deem to be like very natural. So it's kind of, in a way, it's like I don't care much how it looks like. It's natural, right? On this one, yeah, okay. Although I could still see that, you see, at least here, if I try to see it, interpret it directly, at each point at which I anchor, at each point of D, at which I anchor, the dot product between two tangent vectors is some scalar multiple of the usual dot product. So it's not so bad. Although in a way I said, like, okay, I don't care how it looks like, but still it doesn't look so bad. And the scalar, what it is telling you is that these two vectors, when you let your W go to the boundary circle, these two vectors become longer and longer. I mean, the dot product between them becomes bigger and bigger. So when you take the same U, its length becomes longer and longer as you let W go to the boundary circle, to the unit circle. And here, of course, I'm thinking that for every W, I'm identifying its tangent plane canonically with R2, in order to be able to say that the same U somehow lives in all the tangent planes. Okay, I'm kind of making that sort of abuse.
So, sorry, an ignorant question. So this GWD is the pullback of the internal products in
the hyperboloid. Yes, yes,
product.
yes.
So if you actually want a metric to measure distance between points in the disk, you need to do the norm of the difference.
Yes.
Right.
Yes, the norm of the difference for tangent vectors.
Right.
Yes. For a distance, for distance, but all of this in the tangent plane of the circle, right? I mean, it would be the distance between tangent vectors, not distance between points in the disk.
Right.
Yeah. Because this is the Riemannian metric, but not the induced actual metric.
Right.
Okay. Definition of Riemannian isometry, which is a diffeomorphism. So a differentiable function of class C infinity, that is bijective, and whose inverse is also a differentiable function of class C infinity, and with the property that measuring dot product at a point in the domain is the same as measuring the dot product at the image of the point between the images of the tangent vectors. According to what? The only thing that allows me to pass between tangent planes, which is the derivative. Okay, and by definition, stereographic projections are Riemannian isometries between Poincaré's disk and the hyperboloid with Minkowski's form. Yeah. So yet another. Well, this is practically by definition. This is just by how we defined this. And here you can see more nice pictures of how the correspondence looks like. Okay. So that's how we passed from the hyperboloid to Poincaré's disk. Now I'm going to pass to you, and I'm going to do the same. You know, we know that this is just because the pictures I found beautiful. Yeah, but we know that there is a diffeomorphism between U and the Poincaré disk, namely Cayley's transformation. Okay, and now I have a Riemannian metric on D. Well, pull it back to U. Now here somehow the thing is how to visualize. You know, we know how to visualize the path between the hyperboloid and D, is stereographic projection, and somehow it's also nice. It would be nice to visualize the path between U and the disk, and there is a way, and somehow these pictures contain a way of visualizing how is the path, between the disk and U. So you pretty much what you do is yeah, I'm not going to try to do it live because then I'm going to fail. Yeah, sorry. This picture contains the information. Okay. Yeah. So that's what we do to provide you with a Riemannian metric. We just use the Cayley transformation to pull back the one we have on D. Yeah? So here is the definition. And then again, okay, give me explicit formula. Here it is. Again, how can I do it? Well, everything is explicit. The Cayley transformation itself is given by an explicit formula. So one can really do it explicitly. And the point here again, for every point Z in U, if I identify its tangent plane with R2, like let's say standardly, then in terms of those standard coordinates, the inner product of two vectors anchored at my point Z is given by this formula, which tells you it's a at the point Z is a rescaling of the usual dot product. And moreover, the scaling factor becomes larger and larger as Z moves to the I mean, at least when it moves to R, because its imaginary part gets very close to 0, so 1 over that gets very close to infinity. So in other words, for a tangent vector, if it's anchored very close to the real line, it is very long. That's somehow what I kind of somehow deduced from this, at least in an informal way. Yeah. Okay. So now at least we have our 3 Riemannian metrics on three models of the hyperbolic plane, namely the hyperboloid with Minkowski, the disk by pulling back that one, and U by pulling back the one on the disk. Yeah, and then the first thing is to try to describe all the Riemannian isometries, or all the isometries as metric spaces of one of them. At least for the moment, we are not going to do the whole thing. We are only going to see this inclusion. I mean, at this point, one has to stress there are two groups of isometries at this point already present: the group of Riemannian isometries and the group of isometries as metric space. In the end, they coincide. The group of isometries is actually, the group of Riemannian isometries is actually the group of the whole group of metric isometries, but that requires proof. And now the theorem is that if you give me any Mobius transformation that preserves U, then it's an orientation preserving Riemannian isometry. And so in particular is also a metric isometry. Okay, and the proof becomes more or less easy if one remembers this so-called polarization formula, which expresses the dot product of two vectors in terms of just the norm, which is the norm square. The norm square is the norm square of something is dot product with itself, right? So and so it's this is dot product of two arbitrary things in terms of things that are dot product of something with itself, where of course the somethings are not the same, but and this because of this, in order to show that it is a Riemannian isometry, it suffices to show that each of these expressions is invariant on the action of the Mobius transformation, which now is at the level of tangent planes. So if for every tangent vector anchored at a point z, you have this equality, because then you are going to have the corresponding equality for the whole dot product. So let me just describe kind of briefly the process. So we take a matrix representing the Mobius transformation, and compute the derivative at any given point, which is rather easy because it's nu of z is alpha z plus beta divided by gamma z plus delta. So it's really just the quotient rule that one takes. I mean, and now z is in U, so we finally don't have to care about the point at infinity. So just quotient rule, apply quotient rule, and okay, simplify. So that's the derivative. And so the derivative is multiplication by this number. Yeah. On the other hand, like write z as a real number a plus real b I. Yeah, and do the substitution on top. Yeah, and multiply by multiply at some point, which is I think here, by the conjugate of this one, both on top and bottom. So by gamma z bar plus delta divided by gamma z bar plus delta, which is the conjugate because gamma and delta are real numbers. Yeah. So you multiply, you do explicitly the explicit computation just to arrive here. Yeah, and this tells you that that the imaginary part of nu of z, its imaginary part, is just b divided by this other thing. Excuse me. Sorry. Yeah. So, yeah. Why did I compute that? Well, because the imaginary part appears in the computation of the dot product. Okay. So now I do the computation of the anchor that d of dot product of this with itself. So it's you know, I mean, you are seeing it, right? So I take v, I take v, I multiply it with this, yeah, and then the norm square is you know, this comes from the fact that there is a part that is just the usual dot product, and then with the rescaling, yeah, the rescaling. Let me go back here. Yes, so z squared. So what did I do here? I did something. Yeah, no, it's fine. It's fine. At some point, yeah, I was hesitating whether this should be a 4, but it is a 2, yes, because it's just the dot product with a yeah. Okay, and then do some obvious manipulations. I mean, here is like replace the imaginary part with this, and then do the obvious manipulation to arrive to the desired conclusion. So it's not hard. It's just computing the derivative, which is quite easy. It's just the quotient rule, and then do some explicit computations just of multiplications of complex numbers, and that's it. Okay. Yeah, and this was a very short section. Yes. So you see, I'm skipping the other one. The other inclusion, and I'm also skipping the computation of the whole isometry group, which is also interesting.
But they are actually the same.
Sorry?
Like we are not doing it, but they are the same.
No. What happens is that the whole isometry group is so here you have equality actually, and the whole isometry group is so maybe let me write it somewhere here. The whole isometry group is a let's say of Riemannian of U is bless you, a semi-direct product, and this let me see, I always forget, let me see, where I think this is correct. It's a semi-direct product of this with Z mod 2.
You need to know which one is the normal subgroup.
Sorry?
You need to know which one is the normal.
Right, yeah. So this one is the normal, and then, but then still, I still forget, whether I have to use this or this.
Yeah, but the inclusion of the normal subgroup should be the small triangle.
Right.
So this is the right one.
Okay. All right. Okay. Thanks. Okay, so it's a semi-direct product. Yeah, which, by the way, I mean, and if you want, let me write it like this. PSL 2R, which, by the way, I think some people write it like P star SL2R. I think. Okay, so I'm not showing all of this, which is very interesting in any. I mean, yeah. So the shortest curves in U and D. The upshot is going to be in U is going to be the shortest curves are going to be both the vertical line segments contained in U and segments of segments of circle contained in U, orthogonal to R bar. That's the option in U, and the option in D is either line segments passing through the origin, containing D, or circle segments orthogonal to the unit circle, which is the boundary circle. But of course, that's the option. That's the final result. So what does one do? Well, one of the points of having a Riemannian metric is that one can take a dot product of any tangent vector with itself, yeah, and so one can take the norm of that, and so one can define the length of a curve. That's like one of the things, as one was told, I don't know, in calculus, whatever, 1 or 2 or 3. Yeah? One can speak about lengths of curves, and one can speak about the shortest curve joining 2 points. So if I have 2 points, and I consider the curves, let's say of class C1, connecting them, there may be some of them that actually achieve the infimum. Yeah, so the infimum of the lengths among the curves connecting the 2 points. I'm going to call such curves shortest curves, and I will probably just keep calling them shortest curves for a while instead of geodesics, because there is a difference between saying shortest curve connecting 2 points and geodesic. In that geodesic, I prefer to think of it that it's kind of locally distance minimizing, maybe not globally. So whatever. I mean, so actually, geodesics for me kind of are actually solutions for certain differential equation that makes them locally distance minimizing, length minimizing. Anyway, if I just spoke nonsense, then just follow the definition. I'm just going to keep saying shortest curve for a while. Let's work with the connected Riemannian manifold, which is not stated here, but the G distance between 2 points of a connected Riemannian manifold is what you would expect. The infimum of the lengths of all the possible curves of class C1 connecting the points, where one measures the length using the Riemannian metric. And this defines a metric. This makes the Riemannian manifold into a metric space. Yeah. So hence, when one begins speaking about isometries, one has to be at least a priori. One has to be careful whether one speaks about Riemannian isometries or metric isometries. Okay, some computation. So I have 26 minutes. Am I going to make it? Maybe, I don't know. One would like to at least do some computations. So consider a curve connecting the point AI to the point BI with the A less or equal than B. So here, I'm sitting in the upper half plane, and then there is the imaginary the part of the imaginary axis that lives inside the upper half plane, and I'm taking AI and BI, yeah, and I'm asking myself about the hyperbolic length of this this segment, of the segment connecting them. And so I just apply the definition, yeah, and then you know, I just apply the definition to certain parametrizations, to certain parametrized curve connecting them, which is just you know, gamma of t is equal to ti from the interval ab to u. So I do the computation. It's this 1 over t squared comes from the rescaling factor in the description of the dot product in a tangent plane at a point in u. So in the end, I have to integrate 1 over t from a to b. That's just the logarithm, which is logarithm of b over a. Okay, so in the end, fortunately, this length was is kind of simple to has a simple computation. Okay, and now take any curve of class C1, connecting them. So now the second curve delta is any curve, let's say a green one, any curve connecting them. I don't know. It could be like this. And somehow, of course, what I would like to show is that the first one is shorter than the other one under the hyperbolic metric, and it is indeed the case. So one starts with the computation. You know, here this denominator comes again from the rescaling factor. Yeah, this expression, one splits it. I mean, let's say in the denominator comes from the rescaling factor. The numerator comes from the part that looks exactly like the usual dot product of R2. From here to here, I just split, and then I realized that this, you know, here, this part is always non-negative. So the integrand is greater or equal than the integrand here. So the whole integral is greater or equal. You know, I can let the square root go, but of course, when I let the square root go, I have to take absolute value. Yeah, and this, you know, integrating something with absolute value is greater or equal than integrating the same stuff without the absolute value. Okay, and then this I see it's a substitution. I make the substitution, and then it gives me here the logarithm of b minus the logarithm of a, which is exactly this, which is the length of gamma. So indeed, my second curve my first curve is shorter than the other one. Well, less or equal in length, which means that the curve I proposed at the beginning indeed is a shortest curve going from A to B. And actually, I would say the shortest curve. Okay, not from A to B, from AI to BI. Okay, and now what am I going to do? You know, now at least I know for points lying on the positive imaginary axis, I know how to compute the hyperbolic distance between them is the logarithm. It's the logarithm of the quotient of their imaginary parts, and then what else was to say? Yeah, and find the shortest curve. Now, what I want to use this fact to find all possible shortest curves, and now I'm going to use the fact that I know that the Mobius transformations in PSL2R preserve, bless you, are Riemannian isometries, so they preserve the inner product at each tangent plane, and hence they preserve you know, the corresponding integral that one has to take. So so I'm going. So now it suffices to transport the shortest curve that I already found through PSL2R, through the Mobius transformations that preserve U bijectively. Yeah. Okay. But how can I do that? Well, what I want now is to be able to say, if you give me 2 points in U, there is a Mobius transformation that places them vertically on the positive imaginary axis, because then I know that it's actually an Euclidean vertical straight segment, okay, and then I apply the inverse, which then brings this segment to a segment of circle. What segment of circle? Well, I know that the vertical imaginary axis is perpendicular to R bar, so this segment is going to be perpendicular to R bar. That's the whole thing. And then the exercise is to show that for any 2 points in U, there is a Mobius transformation in PSL2R, so preserving U bijectively, that places them where I want. Yeah. So one thing is, yeah. So let me. It's the exercise. I have 18 minutes. Let me give you the description. Give you the strategy very quickly. So the first strategy, the first point is okay. At least one of them put one of them on the vertical imaginary axis. Okay, this I can do through horizontal translations. Okay, that's easy enough. Okay, now I already placed 1 point in the vertical imaginary, in the positive imaginary axis. Okay, the next thing I'm going to do is place it on I. What can I do? I can use multiplication by a positive real number, because multiplication by a positive real number obviously preserves U bijectively. Okay, so I can place it on I. So there is so given my 2 points, there is a Mobius transformation preserving U bijectively that places one of them on I. Okay, now I realize that the Cayley transformation, sends I to 0 in the Poincaré disk. So take this I and send it to 0. Yes, okay, and then why do I do that? I do this because you see, I already placed 1 point on I, and my second point maybe is not on the vertical imaginary axis, maybe it's somewhere else. So I need to rotate it, preserving U bijectively. So the easiest way is to just go to the Poincaré disk, because this goes to 0, and there the usual rotations preserve the Poincaré disk bijectively, obviously. So I can place my point up to rotation in whatever axis I want. So just place it appropriately. So just that when you come back, it's on the positive imaginary axis. Done. So that's what is written here. Okay. So the point was just to realize that there's a sequence of obvious things one can do that preserve the corresponding thing bijectively, and that in the end does do the job. That's the whole thing. Okay, and this allows me to conclude that the shortest curves in U are precisely the either vertical Euclidean segments or segments of circle that are perpendicular to R bar. I already did all the job because I just used the fact that the Mobius transformations that do the job send circles in C bar to circles in C bar and are conformal. So there's really now not so much to do. Yeah. Okay. And again, since the Cayley transformation has these properties that I just said, sends circles to circles, and is conformal. I also know for free the shortest curves in the Poincare disk. Yeah. So I have 15 minutes. Yeah. So I may want to show you some animations about the shortest curves. But, let me keep going, and then maybe at the end or tomorrow I show you some animations regarding that, because I do want to be able to see how the hyperbolic circles look in the upper half plane, mainly because along the way there's going to be a couple of identities that will be essential for Ptolemy's for the hyperbolic version of Ptolemy's identity. Yeah. So exercise, and I would say it's like an essential exercise. This is like an extremely important exercise, which can be done, you know, by just doing everything explicitly. Like for instance, this sort of imaginary. Yeah, sorry, just one thing. So what does this mean that this is invariant under PSL2R? This means that for every Mobius transformation preserving U bijectively. So if you want, in I think I called it Mob plus of U. This is equal to nu of W minus nu of Z square divided by 2 times the image of nu of W, the image of nu of Z. Right? Of course, that's what I mean. And this can be done explicitly, you know, in a way similar to these computations. You know, you just go to excruciating detail, yeah, and you do it. Okay. But it's really important. This is extremely important. I mean, without this, there wouldn't be a hyperbolic version of Penner's identity. Okay, and now, in order to know the circles in U, I mean, I'm going to use an explicit formula for the distance, and actually 3 explicit formulae. So namely these 3. And then, of course, you can say, come on, I mean, with 1 suffices, no? And then I thought this to be the case, and this was my favorite one, until, you know, I wanted to see the proof of Ptolemy's identity in the hyperbolic plane, which use these 2 identities. Okay, so let's see quickly how to prove. You know, I'm going to leave this as an exercise, and then let's see how these 2 are proved, assuming this exercise as a given. So now, for a real number greater or equal than 1, so you see, I'm going to take lambda I, but above I. Well, I want to compute this hyperbolic cosine of this distance. Well, it's hyperbolic cosine of the logarithm of lambda divided by 1, because here lambda is on top. Okay, so that, I mean, this is the computation we made, right? This one is the computation we made of the some minutes ago. Okay, and then the hyperbolic cosine, by definition, is it really by definition? Okay, it's just this formula, you know, it's just given by this, which then I notice, you know, E and logarithm are inverses, so it's equal to this, common denominator is equal, then I get equal to this. And then knowing what I want to arrive at, especially that I want to use the fact that this is invariant on their PSL2R. I kind of I just play a really small dirty algebraic trick, and I notice that this is exactly this. Okay, so at least my proposed formula, which is that this cosine was equal to the corresponding thing, is true whenever I take I and some other point in the positive imaginary axis. Okay, but as we just saw, that's enough because for any pair of points, there is a Mobius transformation preserving U bijectively, placing them in I and lambda I. And let's say if the one that works, the one that we just described, if it grows, my second point underneath, well, I either move with a dilation or whatever, or I perform, or I just exchange 0 and infinity with a 1/z. So it's once one gets used to this, like one sees that this was really just enough. So if you want this done, why? Because the expression, this expression is invariant under PSL2R, under applying PSL2R to the arguments. Okay. For the second formula, it's very, very similar. And actually, once you saw the first one, then you say, it's for the second one, I'm sure it will work. And this 1/2 becomes the square root because there's an exponential involved. And that's exactly what happens. So here you have, and it's I wrote the whole chain of equalities. All of them are elementary, and you arrive to the fact that the desired equality is true again for I and lambda I, and then again what was it? There is something. 1 second. Right. You see here the square of this. You see the square of this is invariant on their PSL2R. So it itself is invariant on their PSL2R. There is one little thing. Sorry, here I overlooked something. Yeah, the square, but here there's Z bar, not Z. Z is outside U. So one has to be, so one needs something more than just this. You see, the square of this is almost this, ignoring the 2. But it's not. So I probably need invariance on C cross C. Okay, so I have to check that. You see, so my proof of the second equality has a gap. Okay, I have to check that. But if I do the same for the sign, here at least I can use, the square of this is indeed this. So at least for the second one, no problem. And the trick is the same. It's the same trick.
So you should have like.
I should have, I should have, yes, yeah, and then there will be no gap. yeah, okay, all right. The thing is, these two are used, as I said already many times, in the proof of Ptolemy's identity in the hyperbolic plane. Okay, and the circles, which now is, I see it now as a sort kind of a byproduct. So let's denote, I have 5 minutes, let's denote, if you give me a point in U and a positive real number, I have now 2 possible circles to consider, the Euclidean one and the hyperbolic one. So this is just notation. E for Euclidean, H for hyperbolic. Yeah. Center that's 0, radius are not. Okay. And the theorem is that if you give me my point in U, then the hyperbolic circle of radius are not centered at that point is actually the Euclidean circle with radius this one, y naught times the hyperbolic sign of r naught with this other center. So you see the radius, the radii are not the same, and also the centers, the Euclidean center is not the hyperbolic center. Consequences. Hyperbolic circles are precisely the Euclidean circles contained in U. That's an immediate consequence. And second, hyperbolic disks are precisely, hyperbolic open disks are precisely Euclidean open disks contained in U. So let's say the topology induced by this metric is the usual topology. Okay. The proof is not hard. Maybe I'm not going to read this. Just how it looks. You see, if you give me the desired center and you compare it to the Euclidean center, so that's the comparison. And here you see here what I did is from each of the Euclidean and the hyperbolic center, what I did is I threw a shortest curve that with horizontal tangent vector at that point, and in order to see how a radius looks like, right? And so the Euclidean radius, we know how it looks like, and this is its length according to the theorem. But the hyperbolic radius goes here to r bar in order to meet r bar orthogonally. Yes. So let me see. I have 2 minutes. So let me see if I can show it. Let me go to Poincare disk. No, upper half plane, circular motion, circular motion, no, geodesic motion, yes, geodesic shortest curves parameterized by arc length, let's say from point to point. So what I'm going to do is I'm going to perform 2 clicks, and it's going to give me the shortest curve from the first click to the second click, but traversed by arc length. So with the constant velocity, with constant speed. So first and second, and then it looks like faster there and slower again there. That's because lengths are very long close to r bar, because of the rescaling factor. Okay. Let me do it with point vector. So now point vector, which is what I did. Now you cannot see that this is tempo scaduto, but which is what I did in the circle. From the center, throw array with certain given with a given tangent vector, which in that case was horizontal. So now I'm going to give, and I hope it works. So my hyperbolic center, and then here is the tangent plane, and then let's say with this direction. Yeah, okay. And then I have to make to say it stop, right? Because otherwise it will never stop. Yeah. So let's say with some other, like more horizontal, like this. Yeah. Yeah. Okay. Now clear canvas, and now let me do it. You know, now suppose we are, you know, like in a pond. You know, I mean, there's a lot of there's water, like a fountain or whatever, but still, yeah. And then you drop a stone, right? And then we know that when you drop a stone, then there is a wave which looks circular, and it's like the Euclidean circles getting far away from the center, which was the point where the stone hit, right? Okay, so now suppose that the surface of that is the hyperbolic plane. How will it look like? Right? And so now that's the point. So again, I fix my point, and now the idea is that you actually see the wave. Let's see. Yeah, so that's how the wave looks like. Yeah. Okay, and then very quickly, no, okay, so it's still in the upper half plane. Yeah, humor me just one more minute. Geodesic segments, how they look like, you know, just. Yeah, I'm just moving like one of the two endpoints. Yeah, and actually on the right, you can see the hyperbolic distance between them. Yeah. All right. So see you tomorrow.